Hi, so today what we want to learn about is transformations of functions. So, in this section, our goal is actually to learn how shifting, reflecting, and stretching actually affects the graph of a given function. Okay, so let's talk about transformation rules. So, in this column, we have how to graph. Okay, in this column, we have how to draw the graph and do that action here. And then in this column, we have how the graph changes our original function f of x. Okay, so first, let's talk about vertical shifts. Vertical shifts, we have y equals f of x plus k, where k is greater than 0. So let's just take f of x to be the square root of x squared, not the square root of x squared. Let's take it to be x squared. Okay, we know our functions, right? So now what f of x plus k says is, it says shift your function up k units. So we would move this graph up k units. And we'd have that. Okay? Now, f of x minus k, where k is greater than 0, says shift f down k units. So take the red x squared and we shift it down k units. Okay? So the graph isn't wider than, it's supposed to be wider than x squared. Then what it is saying here is I'm just illustrating what's happening. Okay? So shifting f up k units adds k to our original function, and then shifting f down k units subtracts k from f of x. Now, horizontal shifts, y is equal to f of x plus h, where h is greater than 0, says shift f to the left h units. So a plus on the inside means go to the left, which is what is the opposite of what you would think. Then in order to do it, we replace x by x plus h. Y equals f of x minus h, where h is greater than 0, says shift f to the right h units. So in other words, we replace x by x minus h. So x minus 6 quantity squared says take the graph of x squared. Now notice that we have a minus 6, so that means move it to the right 6. So we have this is our function. Now, if we want to look at the other function, we would have x plus 6 squared. That would say move it being your x squared to the right 6 units. I mean to the left 6 units. I said to the right, but I meant to the left. Okay? Now, there you go. So, compressing or stretching a graph is done by multiplying. If you want to affect the graph vertically, you put the number on the outside. So y equals a times f of x, where a is greater than 0, says multiply each y coordinate of y equals f of x by a, and it says stretch the graph of f vertically if a is greater than 1, compress the graph of f vertically if a is between 0 and 1. Y equals f of a times x, where a is greater than 0, says multiply each x coordinate of y equals f of x by 1 over a. It says stretch the graph of f horizontally if a is greater than 0 but less than 1, and it says compress the graph of f horizontally if a is greater than 1. So notice that a vertical stretch makes your graph narrow, and so a horizontal compress also makes your graph narrow. So what's happening to the graph is the same as a horizontal compress and a vertical stretch, and a vertical compress and a horizontal stretch. Okay, so the reflection about the x-axis you have y is equal to negative f of x. That reflects the graph of f about the x-axis. In other words, it says multiply f of x by negative 1. A reflection about the y-axis is equal to, means y is equal to f of negative x. So we reflect the graph of f about the y-axis. So in other words here, what we do is replace x by negative x. Now let's look at some examples. So example 1, we have translations of the absolute value of x minus, or translations of the absolute value of x. In part A, we want to graph the absolute value of x minus 5. So remember that the graph of the absolute value of x, we can make it a little bit better, has that corner. We have these lines like so. That's the absolute value of x. Now, the absolute value of x minus 5, that minus 5 is on the inside, so it says go to the right 5 and sketch your graph. The absolute value of x plus 5, the plus 5 is on the inside, so that means you go to the left 5. There you go. The absolute value of x plus 2, this plus 2 on the outside says you take this graph over here and you shift it up k units, so up 2 units. So we go up to 2 and we sketch our graph. The absolute value of x minus 2 says we take this graph and shift it down 2 units. These are straight lines. Okay, now let's look at translations of x squared. Graph x minus 2 quantity squared, and then graph x minus 2 quantity squared plus 1. So we have to shift this to the right 2 because that minus 2 is on the inside. It's a translation of x squared. So we know the shape of the graph. Now, this says shift x squared to the right 2, and this plus 1 says move it up 1. So right 2, up 1, we have this is our vertex, and that's our graph. Okay, wonderful. Now we want to graph translations of 1 over x. And just remember, 1 over x is the reciprocal function, which has the graph as follows. And the other part in quadrant 3. And then we have a horizontal asymptote at y equals 0, vertical asymptote at x equals 0. So translations of this graph, remember that's 1 over x. We want to graph 1 over x minus 1. Well, that x minus 1 is on the inside of the function, so that means we take that function, shift it to the right 1. So our vertical asymptote is now at x equals 1, and that's our graph. And the point at which it crosses the y-axis, that's -1. Remember to find your y-intercept, if that's equal to y. To find your y-intercept, you set x equal to 0. So find your y-intercept, you set x equal to 0. So you would have 1 over 0 minus 1, which is 1 over -1. And that's -1, which means that's your y. Okay, so that's your y-intercept. Now, to graph 1 over x minus 1 plus 1, we shift the graph to the right 1, and then we shift it up 1. So now a horizontal asymptote is different as well. Horizontal asymptotes, remember, has of the equation y equals something, but in this case it's 1. And then your vertical asymptote is at x equals 1. And then we have the following graph. And then this is the other part. Now, what you should do is find the y-intercept here. The y-intercept here turns out to be the origin, but you should verify that on your own. Remember, we just verified the y-intercept for part A. Verify it for part B. That is the origin here. Okay? Now, let's look at another example with several parts, but we're still going to graph. So we're making sure we understand our rules from page 1. We're going to graph negative absolute value of x. Here, this says, hey, you take the graph of the absolute value of x and you reflect it across the x-axis. Okay, so that -1 means reflect about the x-axis, or flip it about the x-axis. Part B says we want to graph 3x squared. So this 3 on the outside, remember 3 is greater than 0. So what this is saying do is saying stretch x squared vertically by 3. So in other words, what happens, remember we can choose specific x values and get certain y. Now I want us to get away from this, right? So technically the graph is really just going to look like x squared, just a little bit narrower, right? Because we're stretching it. A few points with this 3x squared is equal to y. When x is -1, you have 3 times the quantity -1 squared, which is 3 times 1, or just 3, right? So that means at -1, you have 3 for your y. So -1, 3 is a point in your graph. And then when you have 0 for x, that means we have 3 times 0 squared, which is just 0. You have 1. You have 3 times 1 squared, which is 3. Okay, so you have the origin. Then you also have the point 1, 3. And there you go. So it stretches the graph of x squared vertically by 3. Now, part C, you have 1/3 x squared. 1/3 out in front. Notice that 1/3 is between 0 and 1. So that means that it's compressing x squared vertically by 1/3. Remember that a vertical compression is the same thing as a horizontal stretch. Okay, so there you go. This makes it wider. It makes x squared wider. Okay, so if you want, you can plot a few points. Remember, you're getting away from this, but just to illustrate what's happening, you'll have 1/3 times -1 squared, which gives you 1/3. 0, you get 0. And then 1, you get 1/3. So at 1, you have 1/3, and so we can make that better. You actually have your y value is 1/3, your point is 1/3. And similarly at -1, you have 1/3, or -1, 1/3 is your point. Okay? Now, let's look at one that's a little bit more challenging. You have 2 minus the square root of x plus 1. So your basic function here is the square root function. So the square root of x. Okay? That's your function here, your basic function. Now, what this 2 says is, it says move your graph up 2. This minus here says flip your graph about the x-axis. And this +1 on the inside says move to the left 1. So we're going to take the square root of x, move to the left 1, up 2. But then we have to flip this graph right here. We have to flip it. So when we flip it, it's going to look like, well, we can make it a little bit better. That's not the best. We can make it better. Okay? So it has the same shape, but it's flipped. Okay? So -1, 2, that's 1, and this would be 3. How do we know those numbers? Well, again, you know how to find your y-intercept. You set x equal to 0. Okay? So if you set x equal to 0, you get 2 minus the square root of 1, which is 2 minus 1, or you get 1. So that's why you have this point here. And then you know it's 3 because whenever you find your x-intercept, you set y equal to 0. Setting y equal to 0 for us means 2 minus the square root of x plus 1 is equal to 0. Or we have 2 is equal to the square root of x plus 1. Square both sides. And that gives us 4 is equal to x plus 1. Or 4 minus 1 equals x. So x equals 3. That's where that comes from. So that's our graph. Now, the cubed root of -x. Well, that negative is on the inside, but your basic function is the cube root of x. So let's just remember that the cube root of x is this graph. And then the negative on the inside says take that and flip it about the y-axis. So our graph would be this. Okay? One more page. Okay? Let's have a definition here. Let f be a function. F is what we call even if f of -x is equal to f of x for all x in the domain of f. So if we have an even functions are symmetric about the y-axis. Example of an even function, x squared. Notice the symmetry about the y-axis. F is odd if f of -x is equal to -1 times f of x for all x in the domain of f. So in other words, here for an odd function we have symmetry or symmetric about the origin. An example of an odd function is x cubed. Notice the symmetry about the origin here. Okay? Now, in either case, to determine whether a function is even, odd, or neither, you have to substitute in -x for x into your original function. So, example 5, let's determine whether each function is even, odd, or neither. Also determine whether the graph of the function is symmetric with respect to the y-axis. That case you're even. The origin. That case you're odd. Or neither. Okay? So, part A, we have y is equal to -3x squared minus 5. So, we have to find f of negative x, that's equal to negative 3. Remember, we're substituting in negative x for x to find out if we get the original function back or the opposite of the original function. So this is negative 3. Negative x times negative x is x squared. And then we're subtracting 5. But wait a second. This function is our original function, which means when we substituted in negative x, we got our original function back, which meant that our function is even and we have symmetric about the y-axis. Okay? Now, g of x in part B. Part B, we have g of x is equal to the square root of x. G of negative x is equal to the square root of negative x. Or in other words, wait a second. This is neither even because we don't get our original function back. And it's not even odd because we don't get the opposite of our original function. So this is neither. It's not even or odd. Okay? So note, just an aside, negative g of x is equal to negative square root of x. That is not the same thing as g of negative x. They're different, okay? For part C, we have k of x is equal to x over the x squared minus 1. That's equal to, well, it's equal what it is, okay? K, we're trying to determine if the function is even, odd, or neither. So k of negative x is equal to negative x divided by negative x squared minus 1. That's equal to negative x divided by negative x squared is just x squared minus 1. Well, that's the opposite of our original function, k of x. So this means that our function is odd and symmetric about the origin. Okay, and just a reminder, so on the side here, remember that negative a over b written that way is the same thing as negative a over b, and that's the same thing as a over negative b. Okay, all right, so now you know about functions and how to shift them, and you know how to reflect and stretch them and compress them, and you also know how to determine if functions are even, odd, or neither. All right, have a good one.